you load it, and you put the board in. So today it's like doing electronics is something else. And then you have the higher level trigger, which will be all software. So I need to summarize. I have very good muon identification and muon measure for momentum measurement, trigger efficiency, and measure the sign of few TeV muons. That's very hard to do because muon, the higher momentum they have, they will start being straight. So how do you know if they don't curve, if it's a plus muon or a minus muon? So that's like another really simple thing are becoming problematic. This experiment has lots of engineers, lots of physicists, lots of accelerator physicists. Like it's a collaboration with everything you can imagine in there, because you need chemists for a few things, you need physicists for something, you need tons of engineers, computer engineers, and so on. Database expert, how do you record all this data? How do you propagate to all over the world? How do you make sure that the guy in China and the guy in the US can access all the data and nobody is preferred over the other as much as possible? So high energy resolution, you want high energy electromagnetic calorimeter resolution. Hermetic calorimeter means that it has the 4 pi angle and good missing energy. This is like the CERN, and you can see CMS was here, Atlas was here. The question was like, who gets the point? Why is it important? Because here is where the cafeteria was. Everybody was fighting for the cafeteria. So they threw a coin and Atlas won, so they were here, and CMS were here. Everybody was okay, bad luck, but never mind. But what happened, what these guys here didn't think, is that we had to ask extra budget, because the fact that they were here and had to ship everything here and everybody had to travel everything here cost much more money. So, because it's a little bit that's accumulated for all the students, the professors, like everybody. So it's a lot more than it seems, and they're like, oops, we didn't think about it. This is the Atlas detector, and where is the person? Just so that you get a feeling. I cannot even see the person anymore. Do you see the person?
Is he all the way on the right?
Yeah, on the right? Yeah, there's few of them, yeah. Okay, so there's one here.
Yeah.
You see there's few people. This is huge. So just you get a feeling. This is really a huge detector. And the bad thing about this detector is, because they went for L. You remember, they want the momentum resolution to be high. So they went for big L, but it's L cube. So everything costs more. And the thing is that they didn't do like CMS, that was actually much, I like this detector much more, is this one, if there's a problem here, they have to stop, to dismantle everything, fix, put back, which is crazy, as you can imagine. On the other hand, CMS, which was where I worked, you won't believe it how it was. It was, first it's much smaller, and where is the people here? I don't see these people. Do I see here? I can't see the person. I don't know why they didn't put it. Okay, I don't see the person right now, but it's a much smaller experiment, and you can see the actually here, the overall diameter is 15 meter, and the overall length is 21 meter. And the other one, I don't know if there's values here. There are going to be values later. We're going to see how much bigger it is. Behind the barrel? Well, let me move the barrel. Yeah, let me see. Yeah, there has to be, right? Oops. No. Oh, but the size is here. Okay, let's see the size. No, I don't see the size. Did you see?
Oh, yeah, there was one.
Did you see a person?
I think if you go forward one, I think it was one. Yeah. No.
Oh, it's because I'm doing this here. Let me, oh no, it's a picture. I cannot move it.
No, that wouldn't make sense behind the word barrel.
The word barrel.
How do I make slide again?
Like for example or something. I prefer.
from current slide. Okay, cool. So anyway, but this one is only 15 meter diameter, so you can imagine it's not that big. But what's cool about this one is with one finger, if you have a problem, you can push it with your hand. This is tons. It's extremely heavy, but it's all sitting on an hydraulic pad. So you could, if there's a problem, we were able to kind of move it, and you can really literally do it with your hand, move the detector, fix the thing, and close. Excellent engineering here. Engineering is really, it's amazing here. So
There's the person right there.
there is?
Yeah.
Right, okay, it still looks small, but maybe I stretched the picture, but you can imagine this is like 15, yeah, 15 meter is big, but it's not as big as the other one. I don't know where, I forgot to put the other one is huge. I forgot to put the length here. I should add it. But in any case, they use 2 Tesla. CMS used almost 4 Tesla. Resolution of the rest of the detector was about the same. They're very competitive detectors, very different detectors, so it was very good to have. So I won't go over all this. I will continue. Let's see. So we have LHC plan. So the physics, now when I say LHC here was, I mean the accelerator people. So what was their plan? The plan was physics data taking until 2010 will be with 25 to 50. It was usually 50 nanosecond bunch. It was a big shutdown, and they did lots of repair. I don't know if you heard that 2008, I don't know, where were you, in high school? No.
Yeah.
Yeah, so in 2008 there was a big...
We were in middle school, yeah.
High school, middle school?
Yeah, middle school.
Oh yeah, so you didn't hear about it. So middle school there was like this explosion of the detector. There was some quench of one of the magnets, and we went, I think, we did shut down for a while. That was like really kind of... people were not sure if we're going to come back and when and what will be the damage, but we managed to come back. They fixed it. They repaired the defective interconnects. They brought all necessary equipment up to the level needed for almost 7 TeV. They did eventually 6 TeV, and they repaired some helium leaks. Everything was good, and they started again in 2015. And the run was for the first time what was expected to be a 2008. How things are. It was planned to start at 2002 or something like that. It started at 6, 7, it started kind of, 8 really. It started at 8, then there was an explosion, and then we started again at kind of 10 or 11, 10. So that means like, even though your detector is already 10, 15 years behind, when you start you might have trouble and you're another 10 years thrown. So it's difficult. So, and now what they're going for is very high luminosity running. They are running at almost 10 to the 35 inverse centimeter squared inverse second, and they are getting tons of data, 200 inverse femtobar a year. They are hoping to go to high field superconducting magnets, but they are not there yet. And they hope that by 2030, 2033, the energy of the beam will come up from 7 TeV each to 16.5, and the number of, actually it's 14 TeV and, right, beam, okay. 16.5 TeV beam and 76 event per crossing. It's still an idea. I don't know, it's like, actually I didn't check where they are right now. So a few words now on each piece of the detector. So let me see. So we have the tracker. The tracker was the inner part of the detector, right? We had this concentric layer. So this is the tracker totally inside. It's
CMS.
This is CMS, yes. But And you can see actually the beam pipe going into the detector. That's really cool. So CMS is equipped with full silicon tracker, never before. Usually there are like some silicone and some gas that was like a gas chamber. CMS decided to go, everything was very innovative, very ambitious in CMS. That's why I think they did very good. So CMS is equipped with full silicon tracking. And this is basically solid state-of-the-art detector. There's 3 layers and 2 discs of the discs are in the front. And so 2 discs, so when you go in the forward direction, you're able to measure the momentum of the particle, and also concentric layers. So there's 3 layers that are close to the beam pipe. And why do you need layers close to the beam pipe? Because I said that there will be multiple interaction per bunch crossing. And I need to separate between between this interaction, because each one of them is a different event. But every one of them, I really need this next time, but like every one of them will come from a different source. So for example, one will come, and so the 2 bunches are coming with proton hitting each other, but there's 10 to the 11 proton per bunch. So one proton hit 1 proton on the other bunch, and they can collide here, but there's an overlap. So when they're overlapping, one can have the interaction here, one here, one here, one here, and everybody will spray into the detector all these tracks. So I need to separate between the beginning of the event inside this bunch crossing collision. So to do that, what I need is I need to have silicon tracker close to the beam pipe, so I'm able to reconstruct these tracks and see from where they originated. So that's why I need, but I cannot have it too close, right? Because too close, everything is a compromise. I want it very close, but I can't, because too close, what will happen? It will fry, exactly. It will fry, too much radiation. So we will have to change it every few days. So you want it close, but not too close. So you can imagine that every idea, every question that you can ask me, how many students had to answer this question? And that's why it takes years until something starts. Because somebody says, and what if? And what if? Okay, another question, another subject. So you infinite, like basically questions and work and figuring out like this important questions and answer. Then so around the 3 layers come 10 layers in the barrel, which means in the middle of the detector, and an extra 10 layers, and 3 plus 9 in the end cap, which means in the forward detector. So in the forward there will be 12 layers, and in the middle there's the 3 first, and then another 10. And they're also built in a way that like can give you not only the radial, it can give you also some azimuth on where they are. So forgot now how do you call them, axial layer and forgot the word. I would remember. Anyway, so but there are different ways of orienting these strips so that it can give you the XYZ position of this hit. So pseudo rapidity coverage is up to, pseudo basically tells you up to where it's covering. It was almost covering up to 2.4. That's very close to the beam pipe. And transverse momentum has 2 to 3% resolution. Now 98% operational during data taking. Heat efficiency was bigger than 99.9, and that's excellent understanding of the detector resolution. You can see the plot on the left is excellent modeling of the pixel heat resolution. So the y-axis is the transverse impact parameter. So you probably learn what impact parameter is, right? So when you have a collision and a particle is going by, the impact parameter is this distance. So the transverse distance. So so the impact parameter versus the momentum of the track. And you can see as the momentum of the track increased, the resolution is increasing as well, right? And you can see data Monte Carlo, how well we understand. So that's hours of studies and figuring out how to control the noise, how to take the biases out, and how to make sure. And you can see the errors on the plot as well. The plot on the right is measuring the vertex. What's the vertex? Is like when you take multiple particles that are coming from one point, that's the vertex. The vertex is the originating from one point. We call it a vertex. So the vertex resolution, how well you can measure where it's coming from, you can see here versus the number of tracks. And that's very important because, like I told you, there will be multiple events, and in every event there will be multiple tracks per event. So you have hundreds of tracks running around. So you can see that as the momentum increases, the resolution is getting better. And also as you have more tracks, you can see the momentum resolution is improving because you can pinpoint better where it's coming from. Okay, so we'll jump a little bit. You can see here like what do you do? This is actually our daily work. So there is students usually come, and after very soon they say, hey, I want to find the Higgs, I want to find this. But you know, we couldn't give them. There's no way to come and do physics analysis without doing work. So half of their thesis usually is sitting down and taking measurement and understanding one piece of the detector, contributing to it, and his second part is being part of a group that does analysis. So he gets the physics and he gets the hardware. And some students wanted to go into more computing things, some people want the electronics, some people, so there's a space for everybody. But there's a lot of work, and there's a group that's called the particle ID group. And for example, how do I know if what I measured going through my detector is a kaon or a phi or a pion or whatever it is? And you have to basically do the work. So, and you measure it at different luminosity and different interaction per bunch crossing. You just measure and slice it every way to make sure that there's no holes in your understanding, because every hole can give you